So welcome back. In today's lecture, I am going to give brief overview of basis and dimension. Obviously, in order to define basis and dimension of a vector space, I need something more, that is called the notion of a span, notion of linear combination, notion of dependence and independence of vectors. Okay, so with help of these notion, now we are going to see these two quantity, basis and dimension. Okay, and it is possible to show in today's lecture that role of basis is very important whenever we are dealing with any engineering problem. And why that is important? Because in every engineering problem, somehow we are trying to understand the convenient coordinate frame such that I can represent the system. Okay, so for the same system, in today's lecture we are going to see that why infinite many coordinate system is possible. Okay, and once we fix the coordinate system, it is possible to show that representation of each point in that particular coordinate system is always unique. Okay, so these two things are very important, and it is possible to show that most of time if I select the bad coordinate frame, then system looks very complicated. Okay, and it is possible to transfer some more relevant coordinate frame, then same system looks like either not exactly linear system but linear like system. Okay, in that another coordinate frame. So that kind of things also we are going to discuss using today's lecture. Okay, so let us start the today's discussion. So in the previous class I have already defined what is meaning of linear combination. Okay, so suppose I have some kind of vector space, and I have already told you that whenever we are defining the vector space, at that time I need some kind of element or some kind of a scalar that is called field. Okay, so most of time in engineering application, field is real number, okay, or complex number. So I have field, and after that with help of field I am going to stack that scalar either in form of the column vectors, row vectors, functions or matrices. Okay, and after that we are going to define two operations. First operation is vector addition and second is operation is a scalar multiplication, and where a scalar we are going to select from this particular field. Okay, and based on that we have defined the vector space, and during definition of vector space we are going to check some kind of examples. We have already seen this kind of things in the previous class. Okay, and after that what I am assuming that alpha 1, alpha 2, alpha n are the element of vector space. Okay, so whenever you are defining some kind of vector space, at that time I have infinite many element inside some vector space. Okay, now suppose I have select some vector alpha, and if I write like this, it means that this vector alpha is the linear combination of alpha 1, alpha 2 and alpha n, and where this a1, a2, an are the element of this particular field. Based on that this vector space is defined. Okay, so whenever you are defining linear combination, please be careful that whatever the this element a1, a2, an, that should be come from this field. Okay, so that is very important. Now this notion of linear combination is very important. We are going to see several times we have already used during the solution of differential equation. Several places we have already used, but in today's lecture we are just going to externalize that definition. We are going to see that okay, whatever things we are doing, that is nothing but the linear combination. Okay, so remark is that objects that naturally arise in the collection are the large set of vectors that can be obtained from a small sets by forming all possible linear combination. What I am telling, that in previous class we have already talked about this. Suppose that I have two-dimensional space. So this is two-dimensional space, and in this two-dimensional space I have infinite many vectors. Okay, suppose if we are dealing with column vectors x and y, this is x coordinate and this is y coordinate, then you can see that I have infinite many vectors. But it is possible to show that all any infinite number of vectors can be represented just in the finite number of the vectors, okay, with the help of this notion that is called linear combination. Okay, and in the previous class we have already seen that if I will select these two vectors x10 and y01, then I can able to represent xy. Okay, so same kind of structure you can see here. A1 is nothing but, so x here, that is element of some kind of real number. Y I am going to select element of real number. So these two are scalars x and y, and these two are the vectors in this space. So I have just collected two vectors and I am able to represent the any element, okay, inside this space. And due to that reason, idea of linear combination is very important, because they are telling that how to express any element inside that space. Okay, and this is not only one way to represent the linear combination of some element x and y. It is possible to show that even if you will select 1 1 and 1 2, if you check the previous lecture, I have already told you that again I can able to generate any element x and y and here 1 and 2, and here obviously that is not like x and y, x dash and y dash. So you can select any element of this space, and if you solve this linear algebraic equation, you will get the value of x and y, and it is possible to show that using these two vectors again I can represent this same space. Okay, similarly, if you talk about the R3 space, so it is possible to show that R3 is the linear combination of 110 and 120. Okay, so now what we are telling, we know that in R3 space, in order to represent each and every quantity, I need at least three vectors. Okay, and a standard vector in that particular space is like this: 100, y010, and z001. Okay, now suppose someone just select two vectors, okay, and after that they will define the linear combination. So we are going to see that what kind of space that is spanned by basically these two vectors, okay, or covered by these two vectors if I define linear combination. Okay, so if you check it, that set of linear combination, whatever vector I have selected here, that is 110 and 120, so it is possible to show that if vector of this kind of form, then using these two vectors I can able to represent, and obviously I have to scale out by some number. We have to see the solution. Okay, so how to find the solution? We have to find, like here alpha we are representing for vector, these are for vector 110, and after that a2 120, and after that I have to solve x y and 0. Okay, and in that basis I can define a1 and a2. If solution of a1 and a2 exist, then we will tell that using these two I can able to represent this. Okay, now let us try to see one more important thing, that I have already told you that several places already we have used these kind of notions. Okay, suppose I have second order differential equation. This is d2y by dt square. I have defined y double dot like d2y by dt square like this. Okay, so and similarly y dot and y. So if you solve then basically we are searching for two particular solution, and after that we are defining complete solution just by the linear combination of these two solutions. Okay, so individually if I know this solution and this solution, it means, what does it mean? That if I have differential equation, so differential equation, solution of this differential equation is again the linear combination of some functions. Okay, and if I know the function, then I can able to arrive on any solution, and obviously C1 and C2 can be determined based on the initial condition. Okay, so again here we are able to see the use of the linear combination. So what is main motive? That whenever I have some kind of differential equation, and we know the solution of differential equation is functions. Okay, so whatever space that is going to generate by this, that is some kind of function. Okay, now we know that whenever we are talking about functions, so I have infinite many way to represent some function. Okay, now if I select the coordinate frame like e power t and e power minus 2t, or if I will select these two vectors using linear combination, I can able to represent the solution. Okay, anyone has confusion, then please let me know. Now it means that you with the help of linear combination, I can do a lot of things. What is that lot of things? I can able to expand the space. Okay, I can able to move the space. Okay, so same definition I am going to give here, that let V F, means V is the some kind of vector space over field F, be a vector space, and S be a any non-empty subset of V. Okay, then the linear span of S is the set of all linear combination of S and denoted by this LS. Okay, so what basically we are telling, that LS, so here L and this is S. Okay, so what I am telling, what you can do, suppose you have some kind of vector space over some field F, and obviously I have two operation, vector addition and scalar multiplication we are taking, and what basically we are telling, after that you can just try to take some non-empty subset of V, means some finite number of vector you can select, and if you write like this, okay, since a1 a2 and an are the any set of scalars, okay, so by changing a1 a2 an you are able to define the space, some kind of space. Okay, and that linear combination, we are telling that linear combination whatever produced by these combination, that is nothing but the span. Okay, so if you take the example of two-dimensional space, then what basically we are telling, that 1 0 and 0 1 is going to span the whole space, provided if I select x and y as any arbitrary real number. Okay, so in this way we are defining the span of space. So linear combination we are just defining like that. Now we are telling that if I define this kind of linear combination, and if I change a1 and a2 and an, then what kind of space I can able to cover. Okay, that is nothing but the span, we have defined like the span. Okay, and here if you select the spanning set like 1 1 1 0 0 1, okay, so I have three-dimensional vector space, and in this three-dimensional vector space I have selected two vectors. One vector is 1 1 1 and another vector I have selected, that is 0 0 0. Okay, now I want to see that what kind of space is basically spanned by these two vectors. Okay, so a spanning set I have selected these two. Now I have to know the space. So in order to know the space, what I will do, I will scale v1 by the scalar, and here since we are considering the three-dimensional space, so a scalar is nothing but some kind of real number. So if you multiply here with any number, you can see that all three coordinate remains the same, and due to that reason I will tell that only this kind of a space I can span using these two set of vectors. Okay, and obviously that is 45 degree, that is the geometrical interpretation. Okay, among the simplest polynomial vector of form p5 are 1 x square and x4. So now I am going to define the span, and in order to define the span, again you can multiply with alpha beta x square gamma x square. Okay, so if you see the span is nothing but some kind of set theoretical operation that converts set of vectors into other set of subspaces. Okay, so what this is telling, suppose that you have some kind of vector space and you want to generate some kind of subspace. In previous class I have already defined what is meaning of subspace, and at that time what we have seen that, suppose if I have some vector space over field F, and if W is the subset of that, and if that will satisfy all property of the vector space. Okay, so what does it mean? That if you select any two element inside this W, okay, and if that will remains inside the W, okay, and we have seen that in order to check that you can take any two vectors in this space, and after that you can define the linear combination of that two and give guarantee that that linear combination is again remains in the same set. Okay, so basically whenever we are performing a span, okay, so what happens that this operation of a span convert the vectors into some kind of subspaces. Okay, anyone has confusion? Now if you see here, we have talked about the polynomials. Now could you please guess that whenever we are writing the Taylor series expansion of some quantity, okay, so from here you are able to understand that what is the basic idea. So basic idea is that if I have function fx, now what I am going to do, using the basis, and here nothing but alpha 0 1 and alpha 1 x, alpha 2 x square, alpha 3 x cube, like this. So what basically Taylor are good, that if I have some kind of function, and obviously if function has some kind of a specific property, okay, and suppose if I want to represent this function about in some neighborhood, I can able to represent that function with the help of these particular vectors 1 x, x square and x cube. Okay, now if I fix 1 x, x square and x cube, that is our spanning set, then I can able to span some kind of space of these functions. And how to calculate alpha 0, alpha 1 and alpha 2? For that you have to check that at what point point you are going to do the Taylor series expansion. So from here you can see that in order to calculate alpha 0, if you put x equal to 0, then all quantity equal to 0. So alpha 0 I can calculate like x equal to 0. Similarly, now if I have to calculate alpha 1, so alpha, in order to calculate alpha 1, I will take the first derivative. So if you take first derivative, then what happens that here f dash x about x, so this quantity is 0. Now I have alpha 1 and all other quantity is 0 if I will consider again at x equal to 0. Okay, in this way you are able to generate the Taylor series expansion of some function f, provided that is infinite many times differentiable. So we are writing that function like this, that belongs to continuously differentiable function. Okay, then you are able to expand that function in terms of the some kind of spanning set, and where that set contain 1 x, x square, x cube. Okay, similarly if you want to represent fx about x0, then you have to just shift it x minus x0, after that x minus x0 square, x minus x cube square. So main idea is, now suppose if you have some kind of continuously differentiable function, okay, so all continuously differentiable function can be represented about some point if you just know these spanning set 1 x x square x cube, okay, and in this way actually Taylor will come up some kind of expression of this function in easier coordinate frame, and during the linearization process basically we are using the same idea, okay, and due to that reason, in order to understand, because sometimes a student is not able to understand that why suddenly Taylor series expansion can be represented like that. So this is the idea. Idea is whenever I have some kind of function, okay, so I have function, so I can represent that function in form of simpler function, in form of the constant function, in form of, so try to understand like this. I have some kind of function, so I can represent using constant function. I am going to represent using line. I can going to represent using parabola or linear combination of all possible. And obviously x cube x4 has some other interpretation in higher dimensional space. So I can able to represent that. Okay. So by selecting this kind of 1x square x cube vectors that span the whole space of fx about some point, okay, that I can able to formulate, okay, and due to that reason, now you have to understand the idea of a span, okay. So now here, what is our problem? Can two disjoint subset of R2 each containing two vectors have same span? So that I'm going to check, okay, and now question is that second question, what is the span of R3, okay. So now here I have selected means suppose that if I will select 1 0 and 0 1 and 2 0 and 0 2, okay, so here you can see that these two set, what I am telling, that if you have to represent any point, then you can define linear combination alpha or x you can take here, or beta here you can take like this. So you are able to represent any point inside this space alpha and beta. Similarly, if I just scale it out, then also I can able to land up to this same conclusion, that if I select alpha and beta like this, then I can able to represent any point alpha dash and beta dash of this two-dimensional space. But that is not the honest answer, because I am asking that for one set, is it possible to tell that there exist two different disjoint set of vector, okay. Here you can see that honest answer is like this. Suppose that if you select this and if you select this 1 1 1 minus 1, okay, so these two vectors are not just a scaling of first vector, okay, and now if you select 1 1, so and if you solve it, then it is possible to show that again you are able to span any point in two-dimensional space, okay. So it means that if I have two-dimensional space, so I can able to define two different set of vector such that they can span the same space, okay. And similarly, if you select three-dimensional space, so you are already well aware that in three-dimensional space, if I select 1 0 0 0 0 0 1 0, and after that I have 0 0 1, okay, so and if I will multiply with x y and z, then I can able to span anywhere in x y z, okay. So second question is basically giving us the hint that apart from 1 0 0 0 1 0 and 0 0 1, what is another possible set of the vectors such that I can able to span the whole space. And it is possible to show that if you select these three vectors, again you are able to span the same space, okay, and it is not very difficult to check. Now most of time we are using these kind of things, okay, whenever we are talking about Fourier series, okay. Here you try to understand that basic idea is like that. I have some kind of quadratic polynomial, So I can able to represent quadratic polynomial with the help of vector 1 cos x, sin x, cos square x, cos x into sin x, and sin square x. Okay, so I have some kind of quadratic trigonometric polynomial, okay, of order 2 because a square is involved here. So you can see that same polynomial I can also able to represent using cos x, sin x, cos 2x, sin 2x. Just these coefficients are different. And why that is possible? Because we know that cos square x and sin square x is actually related. I can write that sin square x plus cos square x equal to 1. Okay, after that I can actually express cos square x in terms of cos 2x or sin 2x. Similarly, I can able to represent cos x into sin x with help of sin 2x. So in this way, if you see this, then same polynomial I can able to represent using different set of vectors. Okay, so I have same vectors, but I can select the multiple different span such that I can able to represent the whole space. That is the idea. Okay, and due to that reason, coordinate system or representation of one system may be different. Okay, that is the basic idea of the span. Okay, let us see some more terminology, then things become more clear. Okay, so what is the roadmap of today's lecture? What we have seen that a spanning set, we will learn that some subset of vector space can generate the entire space. Okay, so now if we are considering the two-dimensional space, so there is no need to worry about the all vectors. Just if you generate two subset, that is 1 0 and 0 1, or 1 1 or 1 minus 1, we have seen that using two different subset I can able to generate the whole space. So that particular set is called a spanning set. Okay, so basically I have two different spanning set for the same space, 1 0 1 0 0 1 1 1 1 minus 1. Okay, now similar kind of things we have for three-dimensional space, and so that set is basically called a spanning set. Okay, now what is meaning of linear dependent? In some cases the number of vectors in such set are are redundant, meaning we can remove one and more vector without changing the span of the set. Okay, so suppose that if I have to span the three-dimensional space, or for simplicity you can take two-dimensional space. Okay, and in two-dimensional space if I select vector like 1 0 0 1, after that 2 0 and 2 2, suppose if I will select four vectors. Okay, it is possible to show using the four vectors whatever space I can span. If I remove these two vectors, also I can span the same space. Okay, so if I have some kind of set, it is possible to show that some vector can be expressed inside this set. If I select 1 0 two times, then I can able to represent this element 2 0. Okay, so that kind of vector is called linearly dependent vector. Okay, and whenever we are talking about basis of vector space, what we are going to do, we are going to remove all kind of vector which can be generated from this set. Okay, and we are going to select the minimum number of vector, and that minimum number of vector is called the basis. Okay, and somehow that will also gives us the idea of coordinate system. Okay, so I have some object, now we want to represent that object. Okay, so with help of the idea of basis, we are able to understand that how many minimum number of coordinate frame is required such that I can able to represent that system. Okay, so that kind of answer is basically come from the basis. Okay, and we have already seen that in order to span some space, I am able to generate a spanning set in different way. Okay, so due to that reason also, if I have some kind of point, I can able to represent that point, same point, using different coordinate frame. Okay, so let us see this some more definition. Okay, so definition linearly dependent. I hope that you are already aware about what is meaning of linearly dependent, what is meaning of linearly dependent, but just I am going to tell you for the completion that what is the definition, and after that we are going to use this kind of definition to understand. So for example, in today's lecture what we have understood, that why Taylor has thought that some function fx can be written in the combination of x 1 x square x cube. What is motivation to select 1 x square x cube x power 4? Okay, and after selecting, what extra assumption that comes into picture, because we are telling that that kind of Taylor series expansion is possible provided function is n-time differentiable. So in order to calculate the coefficient of that linear combination, they have used that kind of idea. Okay, similar kind of things you are able to think about the Taylor series. You are able to think about the Fourier series. You are able to think about Fourier transform. You are able to think about the Laplace transform. So I will deal that kind of things in the next part of this course. Okay, and at that time I will tell you that what is basis. Okay, what is the span. Okay, so these kind of concept I am going to tell you. Okay, so let us first try to understand the definition of linear dependent. So a vector x is said to be linear dependent upon a set S of the vector if S can be expressed as a linear combination of vector S. So equivalently, x is linear dependent upon S if x is in S, the subspace generated by S. Okay, so this is the definition. Definition is just telling that suppose that I have some kind of set of vectors. So I have vector space, I have collected some kind of set, and if any vectors inside that collected set can be represented in the linear combination of other vectors, then that is called the linear dependent, linearly dependent. Okay, now let us try to see the definition of linearly independent. Okay, so conversely, the vector x said to be linearly independent of the set S if it is not linearly dependent. Okay, and now two vectors are linearly independent if they don't lie on the common line through the origin. We are able to understand these kind of things. Okay, so I am not going to waste much time in this. Just let us come to the condition, that how to check the some vectors. Whatever I have vector space, I have selected some vectors. Now I am going to check algebraically. I am going to check that whatever vector I have taken, so each and every vector is linearly independent or not. Okay, so this theorem will give us the very easy way to check that something is linearly independent or not. Okay, so what they are telling, that a necessary and sufficient. Okay, necessary and sufficient, what does it mean? That if you assume this, then I can tell that x1, x2 and xn are linearly independent. So if I assume from here to here. Okay, another way, if x1, x2 and xn are linearly independent, then it is possible to prove that these two conditions comes into picture. Okay, so both way I can prove. Then it means that A implies B, so you can assume A and then it is possible to derive B. Similarly, you can assume B is true, then you are able to derive A. Okay, so this kind of things basically comes into picture. So now I am going to prove the necessity of the condition. So what we are telling, that suppose x1, x2 and xn vectors I have selected from some space. Now I have defined the linear combination, and suppose that if linear combination is 0, and if that implies that all scalars, okay, alpha k, that is equally 0, then we are telling that all vectors are linearly independent. If one of the coefficient that become non-zero, then I can tell that whatever vector, whatever set of vector I have selected, that is linearly dependent. Okay, so that is the basic idea to check that. Now we need the proof. So proof is very simple. Suppose that if one of the vector, if one of the coefficient of alpha k that is non-zero, it is possible to show that that particular vector can be represented in the linear combination of other vector. Okay, so it means that I cannot able to assume that any coefficient alpha k that is non-zero. That is the basic idea of the proof. Okay, here x bar is not there. Okay, so similar kind of things I have written here. I have just rearranged it, and after that I am claiming that if this is possible, then whatever definition I have given, that is violated. So it means that from the from the contradiction, I can tell that all coefficient alpha k is 0 if vectors are linearly independent. And similar way, I can now assume this, and after that I can prove it. Okay, so this is just way to prove it. Okay, so now what basically we are going to do, whenever I have vectors, then I am going to solve these these things, means this equation, and after linear algebraic equation, and after that just going to check that all scalar whatever quantity that comes into picture, that is 0 or not. Okay, now what is one of the important consequence of this theorem, that vector expressed as a linear combination of linearly independent vector can be expressed in the only one way. What does it mean? That if you fix the linear independent vectors, okay, then after that if you select one particular point, then representation of that should be unique. Okay, so proof is like this. Suppose x1, x2 and xn are linearly independent vectors. So if that is linearly independent vector, then what happens, that I can able to write that k1 and alpha k and xk. Okay, now if this is linearly independent vector, then I am going to select another set of a scalar to represent the same vector. Okay, so since this is linearly independent, same point I am going to represent, and same point if I am going to represent, then solution is only one solution, that is alpha k equal to beta k. Okay, what does it mean? That once if you are in some space, suppose two-dimensional space, and if you fix the independent vector, okay, so what I have fixed, that using these two independent vector I am going to span this whole space, that I have fixed. Then now you can select any coordinate frame, that is p1 p2, and if you try to represent this coordinate frame with help of p1 p2, then I have unique solution p1 and p2. Okay, so if coordinate frame is fixed, then each and every point can be only represented in unique way. Okay, non-unique representation is not possible, and this is very easy to prove. Okay, so now what is main theme, that if I have a space, then I can able to select a spanning set in infinite many possible way. But once selection is over, then representation of each point with the help of the selected span, that is always unique. Okay, so basically that is called coordinates. Okay, so I have selected coordinate frame. So how to select coordinate frame? I have selected with this kind of linearly independent vectors. Okay, and after that, once you fix that, then representation of all point, that is unique. Okay, and that is our requirement also. Okay, so suppose that two students, they have developed some kind of theory for two different systems. Okay, by taking two different coordinate frame. Okay, so finally what happens, that if they will select one coordinate frame and another one will select another coordinate frame, so what happens, that whatever event that is going to occur, somehow those two events should be correlated. Okay, so I can able to make some kind of mapping between that, and that should be 1 1 and 1 2. So that requirement is basically fulfilled here. Okay, now proof is very easy. I have done this kind of proof, so please do not worry about that. So idea of the the linearly independent vector and span together is to define the coordinate system. And once coordinate system is fixed, then I can define the coordinates, and that is unique. Okay, so let us now come to the definition, and this definition is basically combining the idea of linear independent and after that spanning, minimum number of spanning vectors. Okay, so definition that is called basis. So a subset S of a vector space V over field F is said to be basis of this vector space if S consists of a linearly independent vectors. Okay, so you can see here that whenever I am talking about a span, okay, at that time we are not putting this kind of requirement. It might possible if I have two-dimensional space, I can select these three vectors, okay, and I can move whole space. That is perfectly fine. Okay, but what we found that this vector can be expressed in the combination of this vector, so there is no need of this vector, or you can select this 1 0 0 1 and 2 2. Okay, so 2 2 can be generated with the combination of these two. So due to that reason I can able to remove this vector, and if you remove it, then whatever two vectors, that is linearly independent. Okay, so whenever we are defining the basis, okay, so at that time first requirement is S consists of a linearly independent vector. So whatever vector, extra vector that is expressed in the linear combination of all other vectors inside that set, we have to remove it. Okay, after that S generate VF. It means that if you define the linear span or linear combination of these independent vector, so using the linear combination, if you see all possible linear combination, that is called a span. Okay, that can cover the whole space. So same kind of things I have written here. S generates VF, and ls is nothing but a span of vector that is equal to V. Okay, so in this particular example I have this kind of things I am telling that, okay, I have selected these two independent vector. Now if I select an alpha and beta, then I can able to move anywhere inside this space. So set 1 0 0 0 1 0 0 1 is called the basis. Obviously these all are linearly independent. How to check linear independence? That is pretty easy. You can do like this using the theorem. You can do that. What you have to do, you have to express like alpha 3 0 0 1, and after that you can equate with 0 0 vector, and it is possible to show that only one solution I have, that is equal to 0, and due to that reason I can tell that 1 0 0 0 1 0 0 0 1, that is linearly independent. So first requirement is fulfilled, and after that now I have to show that if I select any non-zero element x, y, z, then there exists some kind of alpha 1, alpha 2 and alpha 3. So it is possible to check that that is always exist. Due to that reason I am telling that 1 0 0 0 1 0 0 0 1, that subset is the basis of the vector three-dimensional vector space. So this is three-dimensional vector space where each tuple is some kind of real number. Okay, so in order to represent three-dimensional space, I need three tuples of real numbers. So x belongs to R, y belongs to R, and z belongs to R, and using this linearly independent subset I can generate it. Okay, similarly now you can see that not only finite, using finite element I can span one space. Suppose I have function. Okay, so it is possible to show at that time I have to define infinite set. Infinite set means set where I have infinite many element. Okay, and using that again it is possible to show that I can generate the polynomial over field f. Okay, f you can consider some kind of real number. Okay, so it means that basis may be finite or may be infinite. Okay, so if you see the Taylor series expansion of some function, okay, it is possible to show that fall in this category. But in best case it might possible using 1x and x square only I can represent that polynomial. Okay, suppose polynomial is only of that particular form, or some function of this form only 1x x square. So best case, this is the best case. Okay, but general, if this is most general, so it is possible to show that using infinite number of independent vectors are required to represent this function fx about some point. Okay, now since what we have seen that some space, I have some space, I can able to generate that whole space using finite number of independent vectors, and sometime that vector is finite, sometime that is infinite also. Okay, due to that reason, now notion of dimension comes into picture. Okay, so what we have seen, first you can imagine like that you have some kind of a space contain infinite many vectors. Okay, so it is very difficult to deal with infinite many vectors. So what basically we are going to do, we are going to select some kind of linear combination of vectors such that I can able to express whole vector. Okay, so whenever you are going to define the linear combination, so for that purpose I need some vectors. Okay, that vectors, that independent vectors which is able to represent the whole space is called basis. Now it is possible to show that sometime using finite number of that independent vector I can represent the space, sometimes that is not possible. If that is possible using the finite number of vector, so that space is called finite dimensional space. Okay, and very simple example is two dimensional space, three dimensional space, n dimensional space, because n number of independent vector like 1 0 0 up to n 0 1 0, at least you can guess the standard basis for n dimensional space where each vector is represented by the column vectors. So and last vector can be represented like this. In this way you can generate any Rn space. Okay, so finite number of vectors, due to that reason that is called finite dimensional space. Okay, but if you are considering the general function where I have selected vectors like x power n, I don't know up to what that will turn get, so this is infinite dimensional space. Okay, so functions, if element inside the space in form of functions, that is the example of infinite dimensional space. So let us just check the definition of finite dimensional vector space. A finite set S of a linearly independent vector, you can see that I am talking about just linearly independent vector, is said to be basis for a space X if X generate X. Okay, so first requirement is basis, and a vector space having a finite basis is said to be finite dimensional space. Okay, so using finite number of vector, if I am able to represent the space, then that is called finite dimensional space. All other vector space are said to be infinite dimensional. If that is not, if inside the basis, if I don't have finite number of element, usually we characterize a finite dimensional space by number of element in basis. Thus, a space with a basis of n element is referred as a n dimensional space. We have already talked about that. Okay. Now, what happens that same number of element in finite dimensional vector space. So any two bases for a finite dimensional vector space contain the same number of element. What basically we are telling, suppose you have to represent two dimensional space. So what we found that in two dimensional space, using these two linearly independent vector, using these two linearly independent vector, I can able to generate any point inside this space. Okay, so this is also qualified for the basis because 1 0 0 1 is linearly independent. This is also qualified for the basis because 1 1 1 minus 1 is also linearly independent. Okay, now what is another question, that if these two are basis, means, and if a space is finite, then number of element inside the basis, that is always same. It means that if you have some kind of finite dimensional space, if you select n number of coordinate frame, okay, so number of element inside the coordinate frame always remains the same. That is the idea of finite dimensional space. But in finite dimensional space I cannot comment. Okay, so mathematical proof is very simple. What you can do, suppose that I am telling that I have one space and first basis is x1, x2 and xn. Second basis is y1, y2 and ym, and after that what we have assumed initially that m is greater than equal to n. Okay, so number of element inside the basis is not same. Okay, so now what basically we are going to do, we are going to prove that m equal to n. So how to do that? Since here m is greater than or equal to n, so I start representing each vector x in the linear combination of these two vectors. Okay, and it is possible to show, and after that I am going to replace it. So I am going to represent x1 in form of y1 and y1 in form of all three, because here I have m greater than or equal to n, means this contain a large number of vectors. Okay, and whenever we are talking about basis, then I am telling that using minimum number of vector I can able to span the space. Due to that reason, what I am going to do, I am going to represent y1 by in terms of x1 to xn, and after that what I am going to do, I can replace this x1 by y1, same kind of things I can tell, and using this it is possible to show. Since I am going to represent y1 in the combination of x1, x2 and xn, because this is linearly independent, so I can select different point, but I can able to represent y1 in terms of this. Similarly y2n, if you do the replacement, it is possible to prove that m equal to n. Okay, so proof is just from the induction, so please do this kind of things by yourself. That what you can do, you can select one vector, replace it again. Now second time if you are going to represent, then now I am going to represent in y1, x2 and xn in form of y1, x2 and xn, y2, and similarly similar kind of things if I will do, it is possible to show that finally I will come up to the n equal to m. Okay, so what does it mean? That if I have some kind of a space, so I can able to generate that space using different linearly independent vector. Okay, but number of vector in that spanning set, that remains the same. Okay, and we have already proved that if I can represent some space with the help of the basis, so once you select the basis, then coordinates. What is meaning of coordinates? If you try to interpret in terms of the linear span, then you are able to understand that I am telling that okay, this is 1 0 and this is 0 1. Okay, and this will represent x and y. So these are the vectors. So this vector, linearly independent vector, I have selected from the basis. After that, so my coordinate systems is selected from 1 0 and 0 1, but x and y, that is coordinates of some point, so that is always unique. Okay, so once you fix the basis, then whatever coordinates that comes into picture, that is always unique. Okay, so let us come to the conclusion now. A basis for a vector space V is linearly independent subset of V that generate the V. Okay, so somehow basis is very important notion, because in a space I have infinite many vectors, but basis tells us that how to generate all vectors using finite number of vectors. So if V has finite basis, then every basis V contain the same number of vectors. Okay, but if that is infinite, I cannot able to comment. This number is called dimension of V, and V is said to be finite dimensional. What we have to do, we have to select some kind of set where we have linearly independent vectors, and if we are able to prove that whole space can be generated by that vectors, then now we have to just count the numbers. That is gives us the idea of the dimension. So thus, if the dimension V is n, then every basis V contain exactly n vectors. Moreover, every linearly independent subset of V contain not more than n vectors and can be extended to a basis V by including appropriate chosen vector. So if you have some kind of set, so how to land up to the basis, try to remove some kind of extra vectors, then it is possible to show that finally you will land up to the linearly independent vector that can able to span the whole space. Okay, and in this way I can able to generate some kind of basis of the vector space. Okay, so whenever we are talking about independent vectors, at that time we are telling that no extra vectors. Okay, now whenever we are talking about spanning a space, so what basically we are telling that I have enough number of vectors to span the whole space. And basis, whenever we are talking about basis, then at that time we are telling that not too many, not too few. Okay, so exactly this number of vectors are required to represent some space, and whenever I am talking about dimension, then number of vectors in the basis is called the dimension. Okay, so that is the idea of the linear linear combination, span, linearly independent and dependent, basis and dimension. Okay, and in all next lecture of this course I am going to tell you that whenever you are dealing with something, then idea of basis that comes into picture. Okay, and due to that reason notion of basis is very important. Okay, so with this remark I am going to end the today's lecture. So if you have any confusion, then please let me know. Anyone? Okay, if you don't have any confusion, then I am going to end the today's lecture. Thank you very much.